play a round of Tetris.
Good morning, everybody. Welcome to Advent of Code Day 22. My name is Thomas, and my guests today are Achim and Frank. Good morning, Achim.
Good morning, Thomas. Hello, world.
And good morning, Frank.
Good morning, Thomas. Hello, Achim.
So, Achim, can you explain us the riddle for today? What is the puzzle?
Yes, what is the puzzle? So we're given a list of bricks which have two ends in three-dimensional coordinates. And the first part of part one is these bricks are falling down and we have to stack them up. So more or less we're playing Tetris.
Nice.
And once we did that, we have to determine which bricks might be safely removed without any other brick falling down. So more or less, we're playing Jenga.
So we're playing Jenga and Tetris together. Why? Wow. Why?
Yes.
Yeah. Frank, some comments from your side?
Yeah, it's actually simple as that. So the bricks move in the direction of the z-axis. So this has a special role, this one axis, but then it's straightforward. So we need to find intersections and so on.
Okay, then it's just 3D algebra, matrix calculation, matrix intersection, something like that.
Probably. I believe I did it a bit simpler, a bit slower, but it works.
Yeah. Achim, are you prepared to show me some code for that?
Yes, so I have a run method here, starting with the usual, parsing the bricks, and then let's play a round of Tetris. Thank you. So, first step is we take the bricks and sort them by the z-axis. So smaller these at the bottom, higher these above. The things that haven't landed yet are still dropping down and removing the z coordinate. So I'm starting with the lowest, put them on the ground. Z0 is the ground level itself, so the lowest brick has to lie at level 1. That's why this while loop terminates once the brick reaches level 1. I implemented this very basic. So I create a copy of that brick, remove that brick's z coordinates, and check whether the copy is still above. Yes, is still above the highest already positioned brick. If it's not, and that's why I have this if here, I go into the collision detection. So I have an intersect method on my brick class in 3 dimensions. And if I have an intersection, then my brick B, the original brick, will rest on that brick P that I just intersected the copy with. And also the brick P will then start to support the brick B. So it's a bidirectional connection.
This was the question of the first part, no? Who is supporting which brick?
That is an important thing for both parts.
Okay.
And if I then detect that my brick already rests on another brick, then I don't go down any further and add it to the list of already processed bricks. This is not the fastest approach in the world, but with this simple performance optimization, I got the Tetris method from something like 4 seconds down to a little bit below 400 milliseconds.
So you see,
So,
it's basically not it does not matters much which algorithm is used here. It's so little number of bricks that more or less everything works. Just have to get it right. Yeah.
okay. Achim, can you show us the intersect method?
Yes, it's quite simple. So this is the intersect method, and it relies on a one-dimensional intersect method, which is called 3 times.
Okay, just for every x.
Keep it simple, keep it stupid.
Axis for every axis.
Yes.
Okay, nice. Something else for part number 1?
Yes. The Jenga save remove method. So the question is not how many disassembly can you do on the entire brick heap. That is what I've implemented first. That's why my loop goes backwards to through the pile, because the idea was, okay, I remove the topmost item, then I can remove the item below that, and so on and so forth. No, that wasn't the question. It was the question, if I don't remove any other brick, which one can I remove without producing any damage?
I guess it's important to get the definition here right. So what we actually search for is all bricks that are not a single one supporting another brick. So if a brick supports as the single brick another brick, then we must not remove it, and then we can remove all others. So it's a bit from behind through the ear, but yeah, that's it is the question.
Exactly. Other way around is also, if it doesn't support anything, it can be removed as well.
So, in other words, if there are 2 bricks, if one brick is supported by 2 bricks, then I can remove one of these 2 supporters.
Not necessarily. It's the other way around. If one brick is the only one supporting another brick, then you can't remove it.
Can't remove.
And else you can.
Okay, okay, got it. Nice.
This runs in 2 milliseconds.
2 milliseconds. And for part 1, you were very fast. I heard you were under the first 1,000.
Yes.
Congratulations for that. Nice. Further information for part 1, or can we go to part number 2?
I don't have anything else for part 1.
Then what is the twist in part number 2?
The twist in part number 2 is that in the Jenga phase, we have to do the complete opposite. We have to determine the most destructive ways that we can pull bricks out of our pile. So the question is, so we have to go through all our bricks, and if we remove that, how many additional bricks would drop? We have to do that for every brick and sum those results up.
If you take the first one, everything is dropping, no?
Not necessarily.
It depends. If you have 2 bricks in the bottom layer, it is possible that you can remove either one and nothing else will happen. So they would both score a 0.
Okay.
what you actually do here is creating a list of moving bricks, and you start this list with iterating all of them, and then start with each one. And then if this one is moved out, maybe one other falls, then this other one comes into this list. And then if these two are moved out, maybe some others will fall and you come into the list. And then you go recursively to all of the pile of bricks, and in the end this list has a certain size, and this you have to add to your answer.
Okay. Move to the code, or some more informations before we go to the code?
Yeah. Show the code.
Yeah.
That's more or less it. I know that this can be implemented more efficiently. My method runs in something like 350 millis. I'm pretty sure it can be done faster. So what I'm doing, again, I'm going through my pile of bricks, and I have this set of bricks that are falling or are, so that one brick that I'm removing, I add into the set, and starting from that brick, I go through any other brick that is supported by this one. And there I can check if I remove that brick and any other that is already falling as a result of that, if I kick them out of the equation, will this other brick also fall? If it does, I add it to my will fall set, and I add the bricks supported by that brick to my list of bricks that I need to visit.
By the way, this is a BFS algorithm again.
Yes.
Basically, this to visit here is the queue of nodes that we have to work on, and we always take the first and then loop this around until this list of to visit nodes is empty.
So this year we have a lot of BFS algorithm and no DFS to serve the visits.
These BFS and DFS algorithms always comes into play if it looks like a tree or a graph, and this is all again one with a graph. So these bricks are lay on each other and have edges which say supported by and supports, and from this fact that comes that we have the BFS.
I will also
again.
jump in this method will fall on a removal of. So I put in the entire set of bricks that I have removed or are falling henceforth. I make a copy of my rests on set that I have on that instance. And from that copy, I remove those that are falling down, which may be way more than I have actually inside this one. And then I check if this copied set is empty.
Yeah. To be sure that everything above was falling, or why you need this?
I need that to ensure that everything that this brick relies on is going away.
Okay, I got it.
Pretty short code, but probably not the most efficient in the world, because again, I'm testing again against everything below it that has begun moving one way or the other.
Is there not such a contains all method in this Java sets and vectors? think I remember this. This would be the right method here to use, but it's also quadratic. So if you got two sets with n elements in it, and you call this contains all, and then it must loop the whole set with and combine it with the other set. But
there is, and that is probably a lot faster because I don't need to create a copy. And the rests on set is likely to be much smaller. So this should lead to another speed up.
Okay.
And I remember this because in Rust I searched for this contains all method.
Let's
and I
try
didn't
it.
found it, and I implemented it by hand.
That killed off something like 200 millis.
Nice. Further informations, or is this everything about the riddle?
That's everything.
Frank, do you like this riddle?
No, it was pretty straightforward. So I wondered why the top people take so long. So the first star went away the first place after 10 minutes, and I would have guessed these Python cracks would do it in like 2 minutes or so. But it seems these intersect methods and this sorting by which supports what and so on needs some minutes to settle down in the head before we can write down the code. So I needed more than an hour, even for the first star, because it's pretty clumsy to write down here. It's error prone, all these intersection things. Yeah, well,
Okay.
you see this in the code. This intersect method of Achim has a lot of cryptic signs in it. Yeah.
Achim, same question to you. Do you like this riddle?
I did like it. Hey, we got the chance to play Tetris and Jenga.
Yeah, nice. What was the hardest challenge for you, Achim?
I had a bug in part 2 where I was counting the removed brick as also a falling one, which resulted in a completely irrelevant result.
Okay, and Frank, for you, the hardest thing? Rust.
Actually, I had the same bug as Achim, so the answer was off by the number of bricks. And then I had a bug in my parser, and then I had a bug in my intersect method, and finding all these bugs did take a lot of time. So writing it down was the hardest part.
Okay, then big thank you to you both. And
I noticed a fun fact with the puzzle input. I will show you.
yeah.
Frank, I don't know if it's the same on your side, but it has 1,394 lines. I don't really think that is by accident. Maybe it's a reference to the IEEE standard 1394 named Firewire.
Okay.
Okay, maybe. We didn't know. Okay, 3 puzzles left for the next 3 days. Big thank you to you, and we see us tomorrow. Bye-bye.
Bye.
Bye.